So we are given that a positive charge, big Q, is uniformly distributed along a line of length 2L. So L on this side and minus L on this side, the total length is 2L. And then we have a test charge, a small test charge Q0, also positive, placed on the x-axis at a distance d from that uniform line of charge. The question is, what is the electric Coulomb force experienced by this Q0 as a result of this, of the effect of this big Q? So let's look at a small element of that charge here. So let's say that the size of that element is dy. Let's find out what is the amount of charge within this small element. That amount of charge is equal to dq and is equal to the linear charge density lambda times dy, where lambda is measured in Coulomb per meter. Now, we are said that the charge is distributed uniformly and the total charge is Q. So lambda is then equal to the total charge Q over the entire length of that line. So that's 2L. So we can then say that dq is equal to Q over 2L dy. So this is the amount of charge within this small element. Now this small element creates a small element of electric field at that point. So if you draw a straight line, this is the element of the electric field created by that element of charge. Let's say that this angle here is theta. Now, because of the symmetry of the problem, there is a symmetric element on this side, symmetric to this element. So it's somewhere here. And this element will also create an element of electric field pointing this way. And so the y components of these two electric field elements will cancel each other, but the x components will add up. So in fact, what we need to find is the resultant electric field pointing in the x direction. There will be no y component to it because it will cancel out. So due to the symmetry, it will only have this x component. So what we're actually looking for is the x components of that electric field element. So what is that x components of that electric field element equal to? Well, if you look at this triangle here, dE with a subscript x, which is pointing in this direction, is equal to dE times cosine theta. So it's dE cosine theta. What about dE? dE is equal to k dq over this distance squared. So let's call this r squared. What about cosine? The cosine theta can also be expressed in terms of r. If you look at this triangle now, this angle is also theta, and so cosine theta here is equal to d over this r, d over r. So we can now substitute everything inside. So dEx is then equal to k over r squared, that's this part, times dq, that's this part, q over 2L, and then cosine theta, that's d over r dy. So this then becomes kq over 2L 1 over r cubed dy. So now let's express R. So if you look at this R, if you look at this triangle here, R is actually equal to d squared plus y squared. So d squared plus y squared square root. From the Pythagorean theorem, this is y and this is d. So R is equal to d squared plus y squared square root. And then you can substitute it inside. So you get kqd over 2l dy over d squared plus y squared 3 over 2.
No, 2.
3 over 2. So then we need to calculate for the total electric field. The total electric field would be just the integral of this thing, and we have to integrate y from minus L to plus L. Okay, so the total Ex is equal to the integral of that, so that's kqd over 2L from minus L to plus L of dy d squared plus y squared 3 over 2. Now, in general, in this course, you are not expected to be able to take these integrals. You can just look them up in the table and just substitute for the formula here. So when you look it up and when you substitute everything in, the final answer that you should get is equal to this. So you get k q over d squared 1 plus L over d squared 1 over 2. So that's the expression for the electric field at this position, and the electric field is pointing along the x direction, in the positive x direction. Again, as I said, you're not expected to be able to take these integrals. You can just look them up in the table. So once we found the electric field, we can calculate for the force, and we can write down the final expression for the force. So the electric force experienced by that charge would be electric field times that charge. So this is equal to k q0 big Q over d squared 1 plus L over d squared 1 over 2, pointing in the positive x direction I. There's one thing that you can note from here. If this point is very, very far away along the x-axis, in other words, if distance d is much, much larger than L, then this part here becomes equal to 1, because this is almost 0, so this whole thing is 1. And so the equation becomes F k q0 big Q over d squared. And this is similar to the force experienced by 2-point charges, which kind of makes sense because if you're very far away, from far away this uniform line of charge looks like a point charge. Okay, so everything works out.